Alright, welcome to part 2 of our lesson on 1.5, where we're talking about infinite limits. We're going to go straight into our next example even. We're going to example 3, where we're going to talk about a rational function with common factors. So what we're going to be doing, as we recall from our last video, we've been talking about infinite limits, and so far we have discussed looking at limits from graphs, and then we have most recently started talking about finding vertical asymptotes. So we're going to determine all vertical asymptotes of the function h of x is equal to x squared plus 2x minus 8 over x squared minus 4. So what we're going to need to do first is we're going to want to factor both our numerator and denominator because we're going to see if there's any common factors. I'm going to start factoring my denominator because I know that x squared minus 4 is a difference of 2 squares, so that's going to factor to x plus 2 times x minus 2. And then I have to think. My numerator, x squared plus 2x minus 8. I know that 4 and 2 multiply to make 8, and in some combination, with one of them being positive, one being negative, I can make a plus 2. And in fact, with some of my tricks of factoring, I'm going to know which signs to use. If I look at the fact that this is a minus 8, I need one of these to be plus, one to be minus. My x plus 4 is my bigger factor. It's going to take this middle sign. So I'm going to have this be x plus 4 and x minus 2. And then both the numerator and the denominator do have an x minus 2 in common, so we can just cancel that out. So we're going to have x plus 4 over x plus 2 be our function with our condition that x cannot be 2 because of the x minus 2's that we canceled out. From this, we can take that x plus 2 that is left in our denominator to find our vertical asymptote. If we set that equal to 0, we know then that x would equal negative 2, which means our vertical asymptote is going to be found at the line x equals negative 2. However, x equals 2 is not going to be a vertical asymptote. All that means is we will have a hole in our graph if we were to graph it. Alright, let's go straight into our next example, example 4, where we're going to determine an infinite limit. So let's look at that. We're going to look at the limit of x squared minus 3x over x minus 1 as x approaches 1 from the left. And then we're going to look at the same thing, but instead of approaching 1 from the left, we're going to approach it from the right. So something we can take note of, we are going to have a vertical asymptote. If we were to find our vertical asymptote, we would take x minus 1, set it equal to 0. But we already know if we were to plug 1 in, we're not going to have a limit that exists there. So what we're going to do is we're going to use a graphing utility to graph this limit and determine our two limits here. So let me pull up some graph paper and give you a rough sketch of what this graph looks like. So this is a really rough sketch of our function x squared minus 3 over x minus 1. Let's look at it from both bounds. If we are approaching one from the left, here that I have in blue, we're increasing infinitely. So in this case, our left bound limit is going to equal infinity. And here in the red, as we approach from the right, our x, or our f of x, our y values, continually decrease, which means our limit is approaching negative infinity. So our two answers, our left bound limit is going to be infinity, and our right bound is going to be negative infinity. This then is leading us into our next theorem, theorem 1.15, which we're calling properties of infinite limits. We're going to start this one off by saying let C and L be real numbers, and let F and G be functions such that the limit of f of x as x approaches c is equal to infinity, and the limit of g of x as x approaches c is equal to L, then the following things are true. The first are that we can look at sum or differences. What we would say here is that the limit, if we take our two functions, f of x, and we either add or subtract g of x from it as x approaches c, that is going to equal infinity. Essentially, that's saying if we take infinity and we add or subtract a number to it, we're still going to get infinity. Our second property looks at products. Here we have two scenarios. We have the limit of f of x times g of x as x approaches c. It's equal to infinity when L is greater than 0. And then the whole thing, the limit of f of x times g of x is equal to negative infinity as x approaches c. This happens when L is less than 0. Let's look at our last property. Our last property is going to look at quotients. This property states if we take the limit of g of x and divide it by f of x as x approaches c, it's going to equal 0. The reason being is we're having some number and we're dividing it by infinity, which means it's a fraction that as x continues to increase, that fraction is continually getting smaller and closer to 0. So let's actually look at our last example, example 5, which is going to be determining limits utilizing some of the properties we just discussed. So example 5a, we're going to look at the limit. We know that the limit of 1 as x approaches 0 is equal to 1. But we're also going to say that the limit of 1 over x squared as x approaches 0 is equal to infinity, which you can confirm by using a graphing utility. What we want to know is what is the limit of 1 plus 1 over x squared as x approaches 0. Well, based off of Theorem 115, this is a sum or a difference. We're taking 1 and we're adding infinity to it. That's just going to give us infinity. Okay, let's look at another one. We'll call this one B. We're going to say we know the limit of x squared plus 1 as x approaches 1 from the left is equal to 2. And you can confirm this using a graphing utility. And the limit of the cotangent of pi x as x approaches 1 from the left. Which again, you can confirm this using a graphing utility. It's going to equal negative infinity. We want to know what is the limit of x squared plus 1 over, that whole thing over, cotangent of pi x as x approaches 1 from the left. According to Theorem 115, this is a quotient. We're taking 2 and we're dividing it by negative infinity, which means we're going to be making a fraction that is going to continue to decrease, or in this case, since it's negative infinity, it's going to continue to increase and get closer and closer to 0. So the answer to this limit is 0. Let's look at a couple more. So we have the limit of 3 as x approaches 0 from the right is 3, and the limit of cotangent of x as x approaches 0 from the right is infinity. Which again, these you can confirm using a graphing utility. This is 5c. We're going to ask what is the limit of 3 cotangent x as x goes to 0 from the right. This is a product. We're going to take 3 times infinity. Anything times infinity is just going to give us infinity back. Alright, let's look at our very last one. We'll call this D. We've got the limit of x squared as x approaches 0 from the left. We know that that's going to be 0. And the limit of 1 over x as x approaches 0 from the left. Using a graphing utility, we're going to find that that's equal to negative infinity. If we just used a direct substitution, we would find that that doesn't exist. So graphing utility is what we need to use. We want to find the limit of x squared plus 1 over x as x goes to 0 from the left. Well, this is a sum. We're going to go 0 plus negative infinity, and that's just going to give us negative infinity. That actually is going to wrap up our lesson on 1.5, which even wraps up Chapter 1. So we're going to be having a test on Chapter 1 next week. See you in class.